Hello everyone. Today I'm going to talk about projectile motion part 1. This is the first part of projectile motion where I'm going to talk about dropping objects, launching straight up, and rolling off the edge of a cliff. The part 2 of projectile motion will include launching at an angle, like in this figure shows. I'll explain later what this figure represents. So the first case of projectile motion that I teach my students is dropping a ball or dropping an object. So let's suppose the height of the drop is 20 meters. The time in air can be found using this equation. We know that V initial for something being dropped is 0 because the object hasn't accelerated yet. So with V initial being 0, this term goes away. So then you're left with dx equals 1/2 at squared. In the same problem, we know a is acceleration due to gravity, which, and in this case we're ignoring air resistance, is 9.81 meters per second squared. And the dx is the height that is being dropped. So we know that the height being dropped is 20 meters, so we put 20 equals 1/2 9.81. T is what we're looking for. Solving for T in air, we get about 2.02 seconds. Another thing that could be asked is what will be the final velocity when the ball hits the ground, which can be found using this equation. We know V initial is 0. And A is 9.81, so we find the final velocity to be 9.81 times the time in air, since it's just falling, and then you get the final velocity to be 19.8 meters per second. The other case is launching straight up. So let's say we have a rocket, a toy rocket, of course. We don't expect it to go very high. Let's say the velocity of launch is 40 meters per second, ignoring air resistance. Time to reach the highest point using this equation. Let's suppose that V initial is 40 meters per second, but V final is the velocity at the top, which is 0. Because as the rocket goes up, it loses velocity. And when it's at the very highest point, the velocity is 0 because it underwent an acceleration. The vertical velocity is 0, but in this case, we're launching it straight up. So with the acceleration pointing down, the velocity slows down, it stops, and then it speeds up on its way down. So the time to get to the top, we put 40 for V initial minus 9.81. We need to put the negative in the 9.81 so that 40 will decrease as the rocket goes up. While solving for T and knowing that V final is 0, we get 4.077 seconds. It's the time to reach the highest point. The maximum height reached can be found using this equation. You take the average of the velocities, initial and final, times the time in air. We know final velocity is 0, initial velocity is 40, and the time in air is 4.00077. So we get the maximum height to be 81.5. Now the thing is, time in air, this time is the time to reach the top. Time in air will be the time to reach the top times 2 because it's perfectly symmetrical. The same amount of time that it takes to go up, it takes to go down, so you times the time to top by 2 and you get 8.15 seconds. Now the final velocity when hitting the ground, because as the rocket went up, it's going to come down. You don't have to do any calculations unless you really want to. Is going to be negative 40 meters per second. So you launch it at 40 meters per second up. It's going to come back at 40 meters per second in the opposite direction. The next example is falling from a cliff with initial horizontal velocity. So it's rolling off the edge of a cliff and it's going to follow projectile motion towards the bottom. Initial horizontal velocity is 10 meters per second and height is 30 meters, ignoring air resistance. Time in air using the y component velocity. Why do we use the y component velocity for the time in air? Because what will determine the time that the ball will be falling is the y is the vertical acceleration. There's no acceleration in the horizontal axis. There's only acceleration in the vertical axis, in the vertical component. So we know that when the ball is rolling off the edge of a cliff, at that moment, it has zero vertical velocity. So V initial is 0. The amount of drop will be 30 meters. So this equation just becomes dx equals 1/2 at squared. So you put 30 for x, which actually, it's not really dx in this case, it's dy. 1/2 times 9.81 t squared. Solving for t, we get 2.47. It's how long it's going to take the ball to hit the ground. The next thing is that the final velocity has two components, component y and component x. The velocity in the horizontal direction is held constant. So we know that the particle, the ball, as it falls, it keeps the same horizontal velocity every time, but the y velocity increases on its way down. So we have this figure right here. It's moving to the right to 10, but it's dropping at a different rate every time. The y component of the velocity can be found using this equation. We know Vy initial is 0, and the time in air, which we found time in air to be 2.47. So we're going to put 2.47, negative 9.81, and we get a VYF of negative 24.3. Why negative? Because it's in a downward direction. And we already took care of the negative sign by putting this arrow down. Next is to find the final velocity, which will be the hypotenuse of the triangle formed by the two components. So it's going to be the final velocity will be the square root of 10 squared plus 24.3 squared, which gives us 26.3 meters per second. But a velocity has both magnitude and direction. So we can find the direction, we can find what this angle is by doing inverse tangent of 24.3 divided by 10, which gives us 67.6. But because this angle is below the x-axis, I put a negative in front of that angle. So these are the three, was it three? Let me see, 1, 2, 3. These are the 4 first examples that I give to my students for projectile motion. The next video, I'll share notes with projectile motion by launching at an angle. So this was projectile motion part 1.